That was a great segue. Thank you, Stefan and Paolo, because I wanted to start by saying it's really encouraging to see the support that you are getting from magnetics in Europe, and I would love to see it spread to other parts of the world. We have a new era starting here, of course, so let's see how we can partner together. I was also interested when you mentioned RF detection, because let me just kind of move on to my outline. I have down here fMRID, which is in a way we can relate to some RF detection. And then also when you mentioned pillars of different materials, insulators are hard in the types of nanowires that I'm about to discuss. But actually, Albert Fair, with his partner Perot in Belgium, way back in, I guess, the 90s, late 80s even, had proposed nanowires for GMR and spintronic applications. So although at first I wanted to say, now time for something completely different, doing biomedical applications, there's actually some overlap here. So I thought I'd point that out at the beginning. So without further ado, I will step through this outline and thank Giovanni for the invitation. So I wanted to start off with what I think is a new application for medical materials, magnetic materials in biomedical applications, and that is nanowarming. So I'll talk to you about what that is. Then with that kind of to wet your whistle, I'll get into what is a nanowire, and then show you the results that we have of using nanowires in nanowarming. And just kind of a brief touch on some more standard applications, MRI and isolation of cells and exosomes and so on. And then I'd like to mention some new ways that we've been studying to do identification, some new methods to try to find these signatures of magnetic materials that don't necessarily need contact. Right, so what is nanowarming? It actually is the nanowarming of organs or tissues. And it was driven by my collaborator, John Bischoff, who started actually working on hypothermia for cancer. And some doctors came to him and said, we also have this problem with cryopreserving organs. And honestly, this could be donors, as I'm about to show you, or it could even be someone who would like to separate a couple surgeries where they might want to remove a vesicle from their leg to be able to put in their heart, but they need some recovery time in between. And right now that's not really possible, depending on how long you could preserve that vessel, like an artery. In particular for donations, there's only a 4 to 8 hour transit time for most organs. Unfortunately, I had a friend of my daughter's when she was 22, died in a rock climbing accident in Minnesota, and her organs, she was able to donate to 40 different people, but they had to be basically within Minnesota, Iowa, Wisconsin. And if we could extend the time of preserving organs and tissues, then we actually could impact a lot of other people. And anyone who's interested in donating, should there be an accident, instead of having organs not harvested for use, but actually be used, we could actually potentially have a bank and make sure that we could have immunosignatures so that someone that needs a heart or a kidney would be able to get one that's likely to take. So that's the motivation for nanowarming. So why nanowarming in this particular application? Well, it turns out, just like we've seen so many cell studies just explode since someone figured out how to cryopreserve cells and bring them back to room temperature or body temperature to research, there are ways now, we particularly work with Mass General Hospital, that they can cryopreserve tissues pretty well, and they're still viable when they're cooled. The problem is warming them up. So if you have a tissue like this vessel that's been harvested, and it is viable as frozen to liquid nitrogen, in warming by the standard methods that are used for things like cells, which are very small samples, you can experience cracks or even crystallization of your cryopreservation agent. And so we need a new method to warm. So nanowarming, it turns out, having particles in your cryopreservation agent when it's throughout the organ or vessel and the rest of the preserved fluid, it means that you would have little nano warmers spread out throughout the volume So a magnetic coil could warm evenly and rapidly. That's really the key. Evenly to avoid cracking of the sample, and uniformly as well, so that we can make sure we don't have cracking. But then you also want fast to make sure that you don't crystallize. So I should say, I'm not sure, probably in Italy you don't really have this particular problem, but in Minnesota, in the winter such as now, it's 2 degrees Fahrenheit outside. So I guess that would work out to be, oh, something like minus, let's see, I have to take the 32. Anyway, it's somewhere around minus 10 Celsius. If the lake happens to freeze that you can see through it, which happens sometimes, the ice is transparent, you can see down under. On warming in the spring, sometimes it turns white. And that's because even if something can crystallize without, well, if something can freeze without crystallizing, so it's amorphous, transparent, on warming, you can crystallize. So let's look at what they use for cryopreservation agents. These are basically biocompatible antifreeze. They're not so biocompatible. So the method to freeze is that you would increase the concentration of the cryopreservation agent as you're cooling. That's actually how they're able to get a very good viable freezing of organs and tissues. The question is, how, once you get that high concentration, so it's biocompatible, it's no longer very biocompatible. These are the different cryopreservation, they call them cocktails because they're mixtures of things like glycerol. They have certain properties that have to be met. So first they have to melt, at a decent temperature. And then also this is the glass transition temperature. So you have to get above this temperature at this critical warming rate. They've mastered this critical cooling rate pretty well, how fast you have to cool it. Glycerol, that's why you can't just put in glycerol and freeze it right away. You have to do it too fast and uniformly freezing. But if you can uniformly freeze, like this VS55 is the one I'll be showing you results on, at minus 2.5 degrees per minute, you can have a pretty uniformly frozen tissue. And the key, as I said, is to increase the concentration of the VS55 as you're cooling. Now you have this frozen tissue in the middle of VS55, and you need to heat that uniformly at greater than 50 degrees per minute if you want to be able to avoid crystallization. Now, this work that I've discussed so far is actually from colleagues at my school, John Bischoff, Christy Haynes, and Michael Garwood. And John Bischoff in particular is the lead on an engineering research center that we just got at the University of Minnesota, partnering with Mass General Hospital and UC Riverside. And the engineering research centers are the largest single grant that our National Science Foundation gives. So it's really great to think just last summer, we now have quite a bit of funding to study the heating of magnetic nanoparticles and see if we can contribute to this important field. Here are the particles that have been used to date. This is from that paper by my colleagues. This is Cindy Dennis and some work she's done with Rob Ivkov at Johns Hopkins University. So these are the particles, like this Johns Hopkins University particle is one designed by Rob Ivkov. These are what they're using right now to disperse in cryopreservation agents and then be able to warm and see how fast you can warm. And it turns out the fastest they've been able to warm is 55 degrees per minute, which is barely above that critical warming rate I mentioned of 50 degrees per minute. And with a high concentration, they can get to 100 degrees per minute. So the question really is, will magnetic nanowires heat faster than the particles that are right now being used? So my student and I have this paper with John Bischoff's group where we investigated this. What I'm showing you here are a series of magnetic nanowires. These are very long cobalt iron with gold tips. We grew a little bit of copper at first just to help the growth, and then we break them off, separate them from the template, and that's what they look like. So let's just really dig into what is a magnetic nanowire. This actually is work that was inspired quite a few years ago by the work with Albert Fair and his colleague Perot in Belgium, where they were able to use anodic aluminum oxide templates to grow metal nanowires inside the pores This is an oxide template. So you coat the backside of it, and then you use the backside to electroplate inside the pores, magnetic nanowires, and you can change the component, the concentration, the length, depending on what template you use. You have different diameters available. And we found different ways to kind of image the uniformity of our wires. This is looking at a fracture surface. I actually have this one on silicon, just to say we have grown quite a few magnetic nanowires on silicon for electronic type, magnetoelectronic applications. But in this particular study, I am just growing in free form templates to make sure we could free the nanowires if we want to. Yeah, so here this is just looking at secondary electrons versus backscattered electrons of a fracture surface. So we have our template, we break it and look at the edge. And this is what the templates look like. Anodic aluminum oxide, we have made several very uniform templates in our lab. This is just showing you the length. They're very uniform along the entire length, unless you can play some tricks as you anodize to modulate that length, but we haven't needed to do it for this application yet. Now, we also use track etched polycarbonate, and we have both freed the nanowires to use them. And I should say, we're using nanowires, but we can grow these segments pretty short, as you saw in the previous section. So they don't necessarily need to be long and thin for all applications. But the other application we're interested in is if we use the polymers, we have some fairly flexible polymers, and they are biocompatible because they're used already in things like internal Band-Aids and such. So we're interested to know, can we magnetically enrich that biopolymer and then detect it with the new type of detection techniques, which we're calling fMRID, and also just some ways of measuring a FORC type hysteresis loop. Right, so just some background on the nanowires. I have the papers listed there if you want to see what we do. So here is back to the data. This is back to Daniel's paper with the nanoscale. And the heating actually comes from the hysteresis loop. So it is one thing to wonder about actually with magnetoelectronic applications is what kind of heat is being generated in various structures for other applications. But in our application, we actually want the heat. So a couple things come into play then. How do you increase the area of this loop? Well, if you have a very high MS, you have a high area, and you might want a large coercivity, but you might not, and I'll show you that later. One thing we would really like though is, this is actually a measurement of an array of nanowires. The individual nanowires, we would like them to switch at a single field so that we have very tight control over the switching of each particle. And that's something that we're working on. The reason that we're concerned with that is if you take a look at what's, oops, I didn't know if I had the label there. These are the iron oxide particles that are being used in nanowarming right now. First off, you'll see that the area is much smaller, which you'd expect, even just because they're officially super paramagnetic. But at high frequencies, the hysteresis loop opens up and gives you some area, which gives you some heating. But we know the MS of iron oxide is less than these different metals. And also because it's sort of super paramagnetic, but then at a high frequency, you have a hysteresis loop, it opens out to a very high field. So you can see there's still area to the loop. It's not fully saturated, even pretty high out, like 5,000 Oersted. Our single wires, now we start to see switching because there's interactions between our wires based on the way they're made. But when we separate the wires and measure individually, then we have a sharper switching field. And I will show you here why that matters. This is again from that paper by my colleagues. They did a simulation or a micromagnetic simulation of the field strength throughout their coil that they're using for nanowarming. And you can see that there's much variation in the magnetic field. So they really want to have their artery, or if you have a bigger coil, their heart that you might be transplanting, or a kidney. But how big can you make a coil and switch it at 300 to 600 kilohertz and have still make that really feasible and have a uniform enough field that you can have uniform heating. Because right now, the higher field you apply for nanoparticles, the more heating you get. And that's because you keep circling the hysteresis loop, more and more area of that loop. So coercivity needs to be optimized if you want to have uniform heating in a non-uniform magnetic field. Here are the results. If you want to compare heaters, most people use watts per gram as one measure of how good is this particle versus that particle. So these are the different particles that I showed you on that first slide, and what kind of watts per gram they're getting, specified loss product. So, you see about hundreds of watts per gram iron, but it's important to realize, oh, and these are all at increasing magnetic fields, and it's all of these measurements are at 150 kilohertz. So if we want to take a look now at 40 kiloamp per meter, that's really the maximum that we'd like to use, because we can design a coercivity less than that. Now, it's nice to see actually that nanowires, as far as heating goes, on this measure, when we're comparing particles, are really off the scale, which again, you'd probably expect if you go with a very high moment magnetic material. Now, in reality, when you put this 450, you have to think about, if you're doing watts per gram iron, that actually you have more grams of iron oxide in that same particle. These aren't iron particles, they're iron oxide particles. So if you really compare watts per particle mass, sorry about that, then you're talking more about 325 watts per gram particle. And for iron cobalt, we actually see that if we have randomized particles, we have some very, very high 1150 watts per gram for the at 40 kiloamp meters and 150 kilohertz. And if we align the particles, which can be difficult in some applications, but actually not difficult in this application, because we have these particles free floating in a cryopreservation agent. When we put them in the magnetic, or when we put them in the vial that has the tissue inside of it, we can actually put that vial in a magnet as we freeze it. So we make sure that the particles line up in this all parallel to the field, so that once they're frozen in state and you leave that cryopreserved for a week or so, or as long as you need, then you put it in your alternating magnetic field, the particles are lined up with that alternating magnetic field. And we'll see that effect. This is just one number, but I have it plotted versus a few other things now. All right, so what matters? It turns out that saturation moment does matter. So we've just measured, these are all 8 micron long, and we have nickel, cobalt, and cobalt iron. Iron itself is, it's not always, it's easy to control because it oxidizes more. So our wires may have oxidized a bit, and that's why you'd expect the iron would be somewhere more around here. But if you just look at MS, this is about what you'd expect for the warming of these particles. It turns out that length matters a bit. These are different lengths. This is 3 microns, 6 microns, 8 microns. And concentration doesn't really matter. So we've gone up to 2 milligram per milliliter here, and we've gone out to 10 milligram per milliliter in this sample because our collaborator was thinking we might need that concentration. We've actually shown that 8 microns aligned at 5 milligram per milliliter is actually a really good heater. So what else matters? I'm wondering, I think I see there are comments, but if I could, I'll take all those at the end because I'm not seeing those right away. I just see there is a comment. Right, so heating is what really matters. The SLP is a nice way to compare particles, but when you actually put the nanowires in a cryopreservation agent, how well do they heat the sample? And they have to heat faster than this critical warming rate that I mentioned earlier. So convective heating doesn't do the job. It's gonna, the sample will crystallize on warming, guaranteed, and probably crack as well because the convective heating is gonna heat the outside of the organ faster than the inside. But they did find that with certain superparamagnetic iron oxide nanoparticles, that with 10 milligram per milliliter at 60 kiloamp per meter and 180 kilohertz, that they actually warm. You can see this is actually warming to about, you know, in less than 100 seconds, it warms up to, you know, to basically melt. All right, so let's look at what nanowires do. So I like to say nanowires also matter. And I also like to point out, this is what a nanowire looks like when you zoom back out of it. So I think that some people, when they hear nanowire, they're thinking that's going to get stuck somewhere. It's, you know, you picture almost like a log jam. Again, here in Minnesota, where there's been some logging industry, we've had some rivers jam up. But just remember, they're extremely small. So compared to a red blood cell, that's what our nanowires would look like. And then they warm for an area around them. So the key is to get the concentration low enough that that they're not going to clog, but also, or not even see each other really. So that's the other thing to realize is some of these particles, they see each other and they agglomerate together. So all the coatings that are on the particles are to stop that from happening. Our nanowires have poles on the ends and they actually don't really agglomerate very easily. And we also do functionalize our wires to make sure those ends don't see each other. Anyway, here's how we did. Compared to the critical warming rate, it turns out that the initial rate for a lot of our wires, even at fairly low concentrations, is 1,000 degrees per minute. But to actually get up to the melting temperature, the rate slows down a little bit. This elbow right here is mostly due to the change in the C, the heat capacity of the cryopreservation agent as it goes from being a solid to a liquid. So that's why there's a little elbow here. But I think the key is that even if you take a look at the sample, which is half the concentration of the spions I showed you earlier, we're still at 0 degrees C in less than 20 seconds. So we're really excited to actually optimize this now, right? This was kind of our first shot at it. And now that we have funding through this ERC in Minnesota, I'm looking forward to working on this application more. So what else matters? It turns out uniformity matters. One way to check the uniformity in a vial, if there was a vessel, you would see that in here, is to use something like MRI. So we have actually looked at that a while ago with my colleague Michael Garwood and Valerie Pierre. And we find that our nanowires are actually pretty good MRI contrast agents. So in this application, we might just want to check that, you know, this type of thing doesn't happen at the concentrations that we're interested in so that we get uniform heating. And it's nice to, you can check the sample before you start warming it up and really know what your control is. We've also used our nanowires quite a bit to isolate cells. This is one particular study of separating out some lymphocytes that have a CD4 plus tag on them. So we were looking at, with an immunologist colleague of ours, Mark Jenkins, to see if we could separate out some of these leukocytes or white blood cells that he was interested in studying, and it worked fairly well. And we've also studied exosomes in a paper that I have not mentioned here. So I think I have another 6 or 7 minutes, so I might go a little more quickly through the fMRID that we're working on, because I assume this audience probably has a good idea of what FMR is. Ferromagnetic resonance is the idea that you could apply an RF signal, and if you have a DC field and you sweep that field, there's going to be a certain DC bias frequency combination that has absorption in the sample because you have a resonance of your moment. And that's something to be characterized by this well-known Cattell equation. And this also actually comes from Perot's group when they first investigated nanowires for FMR. And MS and the porosity, if you're actually going to design these wires to not be single wires, so a single wire would have a porosity of 0, but and actually a porosity of 1 would mean you have a film. So we're able to dial in effective fields between single wires, so a shape anisotropy like such and a shape anisotropy of the film. So here's what our measurements look like. At the moment, we're just using coplanar waveguides, so we can do a nice sweep, but there are other ways to try to measure specific signatures. And we varied the way we make our coplanar waveguides. And with my colleague, Rhonda Franklin, this is her student here, first authored this paper, we were measuring the FMR of our samples. And this is that Cattell equation. So like I said, if you sweep the DC magnetic field, you find that the frequency of resonance is going to shift. So here's the different frequencies we're applying and the DC fields at which there was a resonance. So when we combine samples and measured at the same time, the main thing is we can actually separate out the peaks of those different wires, and that's the way to have a bio label. We may even decide to alter the percent cobalt, nickel, iron to make like a barcode where they're all present and we just want to know which code are we looking at. So that's the FMR ID. I hope FMR itself is well known, so the idea of using it for ID is not so contrary to this audience's thoughts. But this, on the other hand, might be a new idea that I'm not sure if you've seen this before. We have several papers. Actually, my student, Reza Zamani, has really worked hard and thought about a lot of different ways that he could put magnetic nanowires as a bio-enriched, a magnetically enriched biopolymer, how he could determine different tags from each other and potentially combine tags to make a specific label. And what he's going to play with is the coercivity, which in particular is from the diameter of the nanowires and the separation of the nanowires. And by playing with that coercivity and interaction field, can he dial in a specific code and find that code among others? And it really comes down to, our first thought was to use something like FORC, first order reversal curves. In that case, you saturate a sample, then you jump to a reversal field, and then sweep back as you measure. Jump to another reversal field and measure as you sweep back to positive saturation, and so on. You just keep generating this family of curves. And there's a way to plot out the coercivity versus the interaction versus the coercivity. But as you can see, it's a fairly complicated signature that you can get out of FORC. And there's a lot of different interpretations of the FORC to try to determine what is the actual coercivity and the distribution in coercivities between the wires or between any particle, and what is the interaction field and its distribution. So with these sheared loops, that can be a little confusing. So Reza has actually studied various ways to project this FORC curve onto the HR axis. So this is the measured, that reversal field. Every time you go to the reversal field, to plot the FORC parameters that you see plotted a lot in FORC measurements against that PHR. We call it the projection method because we're projecting the FORC onto the HR axes. And the other thing he'll do is look at the remnants. After each reversal field is applied, what's the remnants? And long story short, it turns out that remnants is a pretty good thing to look at. And so this is one example of that. I'm just going to list the paper. And he has put his biopolymer into some organs from collaborators of ours and seen that the magnetic properties don't change even without doing anything beyond growing the magnetic particle in a biocompatible, growing the magnetic nanowires in a biocompatible polymer. So it's good to know that maybe this is an option for labeling even an organ as you pick it up and you want to make sure you get that same one, so you track its immunorecord and the donor versus the recipient and so on. There's a lot of applications actually. We can imagine wanting from outside to be able to know what's inside a biosample. Yeah, so this is my conclusion. I hope I've communicated a bit on how we design and synthesize nanowires. And although they sound big, depending, this is a very long wire compared to a Miltenyi bead. And then how we measure them, both by coplanar waveguides and FORC type measurements, and then the different applications that we're using. I think I went a little long, but thank you for the chance to speak to your group.